Alright, welcome to this walkthrough of the second question in the second session's worksheet. This is following the Introduction to Linux session, and this will be walking through that short little capture the flag box regarding Linux permissions. So, the first thing the worksheet tells us to do is get to an environment with Docker. So in my case, I've just got Docker installed on my computer. So I can open up a terminal and run the command that we are given, which is docker run, and then it's that one. So this here means that you want to delete the temporary virtual machine afterwards, and then this makes it so that it is an interactive environment. And then of course here's the actual puzzle image that you want to download. So we go ahead and run that. It might download for you if it's the first time you're calling that command. In my case, it's already found it locally, so it's just immediately opened it. But once we are into the puzzle, which we are now, we can see where we have the puzzle contents there. The instructions we are given are to look for a file with the UID 1000 and the group root. So, in this particular case, our ls is kind of getting us in the right direction, but we can't see a bunch of information just running ls normally. What we want to see is a bit more info about each individual file. So to do that, we can run ls with the l flag. So this will then show us a bit more information about everything. So you can see here, we start with our permissions, which will be very relevant during this session. This is the number of hard links to a file, and it isn't something we need to worry a whole bunch about. Here's your user ID, which is all 1000 for all these, so that's good, that's what we're looking for. And then here's the group ID. So these are 1000 for most of them. However, there's one of these that is the group root. So that's quite relevant, and we'll come back to that in just a second. It looks like the kind of file we're looking for. This next column is the size. In this case, it's in bytes. If you'd like size to be in a bit more friendly terms, you can add the H flag. And doing that will give the ones that are, say, a couple kilobytes in size. It'll put a kilobyte sign after them and switch the units, so they're not just bytes. If there's no unit, then it's still just bytes. So, in this case, this interesting file here, this is the one that we were looking for that has a user ID of 1000 and a group of root. So, if we take a look at that, we can see the file is called favicon.ico. So it's the sort of like website that or icon that you would have on a website. But it seems suspiciously small for an icon like that. See, it's only 107 bytes, and images are usually much, much larger than that. So what we can do is confirm this suspicion that we have that maybe that's not an image after all, using the file command. So with our file command, we can run file, then favicon.ico, and then enter. And then here we get back the result that, well, okay, this favicon is actually not a favicon at all, but instead it's ASCII text. That just means it's something we can read directly. And the way we read text directly, of course, is using the cat command. So we can use the cat command in our favicon.ico and give that a run. So here we get some more instructions. We get instructions that tell us we should look for a file that can be written by everyone, only executed by this certain group 993, and read by no one. So, what we can do in this case is use the find command. This will be very useful throughout this puzzle. So to get a bit more information about this, you can either run man find or find --help. And if you run --help, it gives you all the different options you can use with it. But one that's particularly relevant to us in this particular case is the -perm option. This is actually for finding different permissions on files. So you can give these permissions, I believe, in a couple of different ways, but the easiest way to give them is the 3 numerical digits. So in our session exercise, you can go back and see, I think it's called the octal form. To think about this, let's pull up LSL to help us for a second and then reprint out our message for since we're doing. So we're looking for something that can be written by everyone, executed by a particular group, and then read by no one. So this here means that this file can be read and written by this user. The groups can only read it, and in fact everyone can read it. So each one of these chunks of 3 is something we need to condense down into one permissions number. So if we want something that can be written by everyone, we know that this second bit here, so this second one in, so this last one's an execute one, so you can see that X here. We know that this second one for all of these numbers needs to be active. So that effectively means, because we're treating these like binary numbers, these 3-digit groups, so this is the 1's place, this is the 2's place, this is the 4's place. So we're going to be adding 2 to all of these. So all of these are at least 2, because they can be written by everyone. So we'll have a 2 going in there. Now we want to think about, okay, it can be executed by this group, but it doesn't say it can be executed by anyone else. So we can assume that, okay, it's just executable by this particular group. So if we have in the middle also not an X, so we would have a W and an X in the middle, that's adding 1 to that, so that means that the group number permission would be 3, because 3 reflects this 1 from the execute bit and then the 2 from the writing bit. And then finally, of course, you have read by no one, which just means that this reading bit, which is the 4's place, is empty on all of them. So if we think about that, then we have the write bit for all of them, so that's 2, 2, 2, and then this middle one also has that additional execute bit, which is a 3, or would make it 3 overall, because that's adding 1 to the 2 that's already there. So we can do something, just searching this whole directory. We can do find, then perm for the permissions, and then we can do 2, 3, 2. So the first digit, of course, is the owner, so that the owner can just write it. The group can write and read it, or write and execute it, sorry, and then nobody can read it, so none of these are bigger than 4. So if we go ahead and run that, we get back 1 result. Alright, well that's pretty interesting. We can take a look at some more information of this thing, so say we'll first try, so I'll go ahead and copy that. Keep in mind there's a space here, so that's going to cause us a little bit of grief in a minute. So we can do ls, let's look for some more information on it. And we put it in quotes here because there's a space. You could also just do a backslash to escape that, but I won't bother with that now. So go ahead and run that, you get some information back. So we're seeing that this group 993 actually turns out to be this Koji Builder group, which, if you check our prompt, is the same user that we belong to. So you can double check with something called the ID command what your current user ID and group ID are. So we'll go ahead and run that. And we can see here we belong to this UID, and there's the number, and that's Koji Builder. And here is the group ID. That's what we were looking for, 993, and that happens to be our Koji Builder group. This means, since we ran ID and we got this number back, that means that we belong to this, which is excellent. So theoretically we can execute this file. Now, we can't read it, or although we can write it, but we can't read it, so we could just try executing the file, actually, since that is the one thing that we can do. Now, you might think, well, why would we try and execute this file? It looks like an HTML file. You can't execute that, right? Well, again, you can take a look at the size. Now, the size here doesn't give away a massive amount, because you could have a 17 kilobyte HTML file. That's not unreasonable. But, of course, we can be suspicious because the group permissions allow us to execute it, that it could not just be a regular HTML file. So we'll use file to take a look at it. And if we take a look at it, we see that it's a writable, executable, regular file with no read permission, which is exactly what it told us a minute ago, but the important part, of course, is the executable. So then, to execute something in Linux, you just run it with, or just give the file name with no extra command, although you'll need to make sure that you have a / or something at the beginning indicating that's a path. And then you just click enter, and you can give it a run. And hey, we get something printed back at us. So, oh no, we've been pranked, misled again. So now we need to look for a file with the same permissions as navmenu.js, but in a hidden place. Well, first of all, we should probably figure out what in the world is navmenu.js. Now, we could just manually go around exploring with ls and cd to look around different places. We could think, oh, well, it might be in some place called assets. Then we could do an ls and see, you know, oh, there's a JavaScript folder, and get there that way. But you might need to guess a little bit to do that, and that's sometimes not the easiest thing. So a better thing to do is to fall back on our friendly find command. So if we go back to our find command, we can see that there is actually another option that we haven't played with yet. So that one is the name option, which should be somewhere around here. We have a user that'll give us a name. Aha, of course, there's name. So name and then some sort of pattern. So in this case, our pattern can just be the name of the file itself. It doesn't have to be anything fancy. So we were looking for a navmenu.js. So let's try name navmenu.js. Oops, nearly. And we go ahead and run that, and we see, oh, well, there it is. We were on the right track before. Here's an assets.js. So of course, well, it's a JavaScript file. Can't we just take a look at that? And of course we can. So we can just do a cat, paste it in. But you see, oh, we can't read it. Well, that gives an indication as to what the permissions are. So if we want to get or check for certain what these permissions are, we can use our file command. So using file, our old friend, or sorry, not file. You could use file, because here you can see that it's executable and with no read permission. But if we want the more specific information, we can try ls long, so with the L. Here, we can see, very interestingly, it's writable by everybody. Well, actually not everybody anymore. So it's writable by the owner and by the group. It's also executable by the group. But other people can only execute it. No more writing for them. And the execution permission is actually new in itself. So if we think about what the number for this would be, for our last digit, I guess we'll go the other way. So if we go from left to right, our first digit, we have nothing in the 4's place, one thing in the 2's place, and nothing in the 1's place. So this is going to be a 2. Here, this will shake out to be a 3, because you have a 2 and a 1. And here, you're going to have no 4, no 2, and then just a 1. So that'll end up being a 2, 3, 1. So that's the permission of this particular file in the numerical form. So now, if we recall our instructions, which to be fair are a little ways away, we're looking for a file with the same permissions as that, but in a hidden place. So hidden files in Linux are preceded by a dot, but first we'll do our search, and then we can see, and we can narrow that down. So if we do find, and then permissions, and then that permission number, run that, we get back two things. So of course, the nav-mini.js, which we just found a second ago, but also this hidden file, .git. So it's hidden because if you run ls regularly, you won't see this .git folder anywhere. In fact, any file name starting with a dot in Linux is automatically hidden. But if you want to see those hidden files, you can use -a, and that -a means show me all of the items. So if you run that, you see, there's a couple of hidden files actually. So these two, this actually just stands for the current directory, and that's the previous directory, so you can move upwards. Here's that hidden folder that we just found with our find command, and there's another hidden file here, but that doesn't seem to be of much interest to us at the immediate moment. It's just a regular Git file. So, with that in mind, we can now take a look at this file here. So let's learn some more about it. We'll run ls with L for our long information, give it a bit of info. We can see that, well, it seems quite large, so that's, if we pass on our H, I think that'll be the same 17 kilobytes that we saw in our previous one. Yep. So that one's another one that's 17 kilobytes. Obviously, we know the permissions could be found them just earlier, but it's no longer owned by the Koji Builder group. The thing that allows us to execute this, even though we're not part of the group, we're not group ID or user ID 1000, is the fact that everybody can execute it. So, given that everybody can execute it, we should probably try executing it. So I can hop back to the beginning, and then just run this. That'll try running the file itself. Press enter. It says, aha, well done finding me, but I'm not giving up my flag that easily. If you want my flag, you're going to have to read .cache. Well, where's .cache? Well, we can try our same trick we tried before with our name and our file, do .cache. And well, that's convenient. It was in the same folder as our flag executable that we just run. So let's jump over there, because that seems mighty. It's good to be close by. So we can use cd and then paste in that directory. Now we're there. We can run ls to see what's going on. And there's nothing there. That's rather strange. But you need to remember the thing with hidden files. So if we look back at this file name that was returned earlier, you can see there's a dot at the beginning of this name. So we can recall what we did earlier, which is to use a -a at the end of it. So -a to show all the files, and hey, we get a number of different things there. Now if we want a bit more information, of course, we can toss in our other options, and then here's a pretty helpful readout. So we can see here's .cache, but immediately it seems like there's a bit of a problem. No one on the system can read .cache. With the exception, of course, of root. Root can do anything on the Linux system, but we are not root, and we don't have a way to get there, at least not yet. So, in this case, what we need to do is look elsewhere, essentially. But quite promisingly is this other thing in the directory called cache cracker. Well, that sounds rather convenient, doesn't it? And you may notice something very, very strange about this readout here, and that is that there's this S option. So what this S option here is, or this S permission, is the set UID bit. So what this means is this gives this executable. We can verify that it's an executable with file, but they use things with that set UID bit are almost always executable. So we can verify that. .cache. Oops, there we are. Cache cracker. And we can see, yes, it looks like an executable, so it's an elif object, and these elif objects are binaries in Linux, and you can see it gives us a bunch of other information about it. So if we want to, so we know that this thing, since it's a set UID and it's in the owner slot, and the owner here is root, that means that this executable can change its own permissions to be root. So this is an excellent loophole that we could use to gain, at least if we could exploit this program somehow, root permissions on the system. So we might as well run it and see how easy it will be to actually exploit this binary. So we can go ahead and run cache cracker, and well, that seems a bit easier than we could have feared. So we have, howdy, I can change the permissions on .cache. Well, that's convenient. That's exactly what we want to do. So then it asks, of course, which permissions would you like? Well, let's just put in, I don't know, something to test here. We can put in 3 1s or something, right? And it tells us what command it runs. So it ran this chmod command, which can modify the permissions on files. And here it set those permissions to the numerical permissions 111. And it's done that to .cache. So we can verify the changes made here using our ls command again. Now we see, the permissions on .cache have changed to 111. You can see that because you have the executable bit lit up on all of them and nothing else. So that's just the first bit that's being lit up. Now, the last thing to do here is to think about, well, what permissions actually let us read .cache, and ultimately that just means we need a read bit set. And we'll need the read bit set for the anyone group, since we are not the owner or the group, because we're not root. So in that case, we're going to set this last octet so that we have a read bit set, which is this 4th bit here, so that's just a 4. So we can do anything 4 or greater. In our case, let's just do cache cracker. We'll give ourselves the minimum possible permission, so everybody else can do nothing at all, and we can just read the file. So if we go ahead and run that, and then we run our ls, we can see, aha, that's exactly what we were going for. We can read it now. Now, can we actually read it? Well, there's only one way to find out, and that's by trying. So we can do cat, and then cache, and then there you are. There's our flag. You finally captured it. You've made it to the end of the level, and you found your flag. So, well done if you've made it that far. If you got stuck anywhere along the way, hopefully this will help unstick you. But if you have any questions, of course, feel free to ask at our next session. But yes, well done if you found the flag, and no worries if that was a bit tricky. You're well on your way to mastering the Linux command line.